Thanks, Carl, for the introduction, and good morning, everybody. As Carl mentioned, I'm from the physics department, and the main objective of my talk here today is to share with you that quantum computing, and more broadly, quantum information research, is actually a cornerstone of the physics department here at UMBC. And there's a large number of faculty and a very large research enterprise, both experimental and theoretical, going on in the physics building just on the other side of a campus here. If you want to learn more about anything I'm saying, you can just go to our website, search on quantum computing, and you'll see everything I'm talking about. Okay, so in the physics world, we're what's considered a mid-sized department. We have about 20 regular faculty, 10 research faculty, roughly 50 PhD students, and about 150 undergraduate majors. Our research areas in the physics department are fourfold. So we have research in atmospheric physics and astrophysics, as well as condensed matter physics. And what I'm here to talk about is our research in quantum information science. So we have 5 faculty members doing research in this area. Before I get into their specific areas and what they're working on, I wanted to take a step back and tell you sort of an overview of quantum computing, maybe a little bit from a physics point of view. So the history of this field, roughly speaking, goes back to the early 1980s, and there was a physicist named Richard Feynman who was actually trying to simulate a very simple system of a few electrons interacting with one another. So picture little particles colliding, and where will they go, and how do I model this? And what he found was, after he got up to a size of more than a few electrons, the problem became essentially impossible to simulate on conventional computers. And the reason, as Andrew mentioned earlier, was because the electrons need to be described by quantum states. There's this 2 to the n scaling, and the problem gets very complex very quickly due to these quantum effects. So Feynman, being the very smart guy he was, he sort of turned the problem around and said, okay, let me imagine I had a computer that operated based on these interesting quantum effects. What could it do? And so to make a very long story short, over the last 20 years or so, what we found is that these computers would be very good at quantum simulation, simulating complex quantum systems, quantum chemistry, and so on, as well as some very specific algorithms, one known as Shor's factoring algorithm, which has to do with factoring huge prime numbers, very relevant in encryption and data security. Grover's search algorithm, which has to do with searching unstructured databases. And finally, quantum supremacy, which is sort of a hot topic now, where we're actually pushing towards demonstrating systems that demonstrate a clear advantage over classical computing systems. What's going on with quantum computers from a physical point of view? Well, there's kind of a principle elaborated by Ralph Landauer, and it's a very simple statement that information is physical. And it's a seemingly simple statement, but it actually has very deep philosophical and physics implications. And roughly speaking, what this means is that it's not enough to think about zeros and ones as abstract quantities that are just sort of out there. These have to be represented by physical systems, processing the information, storing it, deleting it. This takes energy, it takes work, there's entropy involved. These are physical systems that have to be described by the laws of physics. And so in one regime, we have classical computing, where we have classical bits that are represented by big classical objects that obey the laws of Newton and so on, things like wooden beads on an abacus, all the way to large voltage pulses representing the zeros and ones in your cell phones. On the other extreme, the idea with quantum information is, what if I can represent true quantum systems to encode this information? So what if the information is represented in the form of single atoms, single photons, and so on? And in that case, as Andrew, I think, described very well, we end up with this idea of a quantum bit or a qubit, which is actually what's something known as a superposition of 0, 1. In a very abstract sense, it's as if it's 0 and 1 at the same time. And so this leads to concepts like entanglement or correlations between bits that are simply stronger than classical physics allows, and is essentially at the heart of the power in quantum computing. So from a physics point of view, it all comes down to what physical systems can I use to represent these qubits? What do I have the tools and technology in the lab to actually build and work with these tiny little systems to implement these qubits? And so there are a number of platforms currently being investigated today. A few are shown here. The first is what we call spins. So if you picture a little top spinning one way, that would represent a 0, spinning another way, that represent a 1, and I can have superpositions of those in quantum mechanics. The second is superconducting circuits, which is essentially at the heart of the IBM system we already heard about, where in this implementation you can picture a current flowing in a loop one way or flowing in a loop another way, representing the zeros and the ones. Trapped ions is a very interesting approach where we essentially picture atoms with different energy levels, and the lowest state could represent a 0, and the excited state could represent a 1. And finally, photons, which is my own area of expertise, where, for example, the polarization of a photon, being polarized one way versus polarized another way, could represent these 0s and 1s. So these are all viable systems where around the world there are a number of groups working on these approaches, where we're developing tools and technology to get down to the quantum level and demonstrate these quantum information protocols. In our own department, the 5 faculty I mentioned, just to go through them very quickly, the first I want to mention is Jason Kessner. He's a relatively new faculty member. He joined the department about 6 years ago. He's a theorist, primarily focusing on spin qubits, but more broadly on an area called quantum control. So this is kind of related to the idea of using feedback and feed forward in circuitry, if you will, to implement quantum error correction and control the errors in these quantum systems. The second group is comprised of myself and my colleague Jim Franson. We're working with photon qubits, so single photons or particles of light to do these quantum operations. And so it's a remarkable system to kind of calibrate you. A single photon is a really tiny thing. Coming out of these light bulbs are something like 10 to the 25th photons per second. We're doing experiments with 1 photon. So this is a completely crazy area of physics with a lot of interesting surprises and fun to work on. The fourth faculty member I'll mention is Sebastian Defner. This is the newest addition to our department. He arrived in 2016 and has already been doing all kinds of wonderful things in a generally broad area called quantum thermodynamics. So his research essentially covers all of the qubit approaches from the sense of how much work is needed, how much energy is consumed, what are the speed limits, how fast can we process these informations, what is it really going to take to achieve quantum supremacy, what are the physical resources. And finally, I want to mention Yanhua Shi. He's sort of the most senior member in our department in the sense that he's been here since 1990. He's one of the pioneering research members of the physics department, and he's best known for something called quantum imaging, which is an area using quantum information processing techniques to basically take better pictures, higher resolution, better microscopy, better lithography, and so on. So again, kind of a quantum information advantage over classical systems. So that's it. That's just a very brief overview of what we've got going on in the physics department. I hope I've left you with the idea that there's a lot of quantum computing research going on over there. We have 5 faculty members working in slightly different areas. We're all interrelated and collaborative. We have PhD students, undergraduates, and it's great to introduce myself here. We're looking to collaborate and look forward to getting to know some of you a lot better. So, thank you.